Okay, so I'm very excited because today I'm going to talk about one of my favourite topics, which is natural transformations. So what are they? Okay, well, here I've got a kind of picture of part of this category of categories. I spoke about this in my video, Functors and the category of categories. So the idea is that this itself is an enormous category, and it has objects, these sort of dots here, and these dots represent categories. Okay, so the objects are categories and the arrows are functors. Remember, a functor is a sort of category structure preserving mapping that allows us to compare one category with another. Okay, so we have this enormous structure, and it's just a very, very interesting kind of thing. However, in that earlier video, I wasn't really able to do justice to the whole structure of the thing, because all I could talk about at that point was the objects being categories and these arrows being functors. The idea of a functor allows us to compare these categories, allows us to compare all these different structures, recognise patterns and so on. It's a very, very important idea. But the central kind of philosophy of category theory is that when you have an important sort of mathematical object, such as the idea of a functor, why not think of those as objects and then think about what the natural kind of arrows might be between those objects? So it turns out that the natural kind of idea for an arrow from one functor to another is a natural transformation. Okay, so I'm going to tell you the definition of it, but let me say something first about why natural transformations are so great, in my opinion. And one reason is because it allows us to understand a lot more about this structure of this kind of category of categories, which is just such a rich mathematical structure, and it really seems a lot kind of high dimensional and interesting when you know about natural transformations. And I mean, another thing is just the definition of a natural transformation itself, because it's defined not simply as an arrow from one functor to another. It's actually defined in terms of the kind of goings on in this source category C and target category D. And so it has kind of many levels of interpretation. We can think of it in these kind of global terms, but we can also sort of zoom in and think about how this natural transformation is working within these actual categories, particularly in this target category D here. And being able to do that gives us a kind of view of category theory from sort of multiple perspectives. And lots of great ideas in category theory or important proofs involve this kind of shifting from one perspective to another, jumping up and down levels of abstraction. And the natural transformation is really a kind of something like a kind of conduit that we can use to move between levels of abstraction. Another crucial reason to learn about natural transformations is that they're just used all over the place in category theory. I mean, they encode an enormous amount of information and some very elegant sort of relationships between things in a very, very succinct manner. So just a few sort of a sentence or two talking about natural transformations can have an enormous amount of content, and we can always kind of open up the lid and see what these natural transformations are doing inside these categories. And it really we see that there's an enormous amount of kind of structural information that can be communicated with this concept. So it's really a very, very useful kind of language tool. And we're going to see later that so many interesting ideas from category theory, like notions of limits and adjunctions and monads and all sorts of things are discussed in terms of these natural transformations. Okay, so here comes the definition of a natural transformation. So if we have a pair of functors f and g, which both go from C to D, then we might have a natural transformation alpha, which goes from F to G. So that's one way you can think of a natural transformation, but of course I haven't really told you how this arrow between functors is defined. And it's actually defined in terms of the goings on within these categories C and D, in terms of the arrows and objects of these categories. So I've drawn an example category C and part of an example category D, and I'm going to show you what a natural transformation between them looks like. So I'm saying if we have a couple of functors f and g and they both go from C to D, then what a natural transformation really is it's a family of arrows. So for every object I in the category C, well, this object's going to get sent somewhere under F, and it's going to get sent somewhere under G. And we want there to be an arrow from where it got sent to under F to where it got sent to under G. And that's going to be the so-called ith component of the natural transformation. So for every object I in our source category, we want there to be an arrow alpha I from f of I to g of I. So that will be the ith component of the natural transformation. And we're going to have one component of the natural transformation for every object in this category C. So J gets sent to f of J under F, and G of J under G. And so the Jth component is going to go from f of J to G of J, and the kth component will go from f of K to G of K. Okay, so I mean what the natural transformation really is it's a family of arrows in this source category, which conveniently kind of represent the sort of displacement between these two, between where stuff lands under these two functors. Okay, but there's one more thing that we require, and that is essentially about the way that the family of arrows works with respect to the way that these functors map the arrows of C. Okay, so basically the second requirement for a natural transformation is that for every arrow F, so we have an arrow F from an object I to an object J, well, under this functor capital F, that'll get sent to this arrow here, and under this functor capital G, that'll get sent to this arrow here. And we want this kind of square here to actually be a commuting diagram. Okay, so going along this arrow and then this arrow will give us the same result as going along this arrow and then this arrow. Okay, so this is a kind of extra condition which completes the definition of a natural transformation. So what I'm basically saying, maybe easier if we talk about it with a separate diagram. So let's say we have an arrow F in our category C, which goes from I to J. Well, in that case, under our functor F, this will get lifted up here. It'll be an arrow capital F of F from F of I to G of I. And under our functor G, it'll get sent to this arrow down here, G of F from G of I to G of J. Now, for this object I, we have, here's the ith component of the natural transformation. And for this object J, here's the jth component of the natural transformation. And so we have this square, okay? There's two different ways in this square. We can go along f of f and then alpha j, or we can go along alpha I and then g of f. And I'm saying that we require, in order for this to be a natural transformation from f to g, we require that this square commutes. So what does that mean? Well, it just means that alpha j after f of f has to be equal to g of f after alpha I. And we require this condition to hold for every arrow f of our original category. Okay? So the way I like to think of natural transformations, I like to try and give things a sort of geometric interpretation, but this is just for personal intuition. I don't know if it's helpful to everyone, but the way I like to think of it is that, let's say we have some structure in our original category. Well, we send this structure to something under F, and we send it to something under G, and then the kind of natural transformation is going to be a family of arrows from where stuff gets sent under F to where stuff gets sent under G. And in some very fuzzy sense, we're sort of thinking of these arrows as being kind of orthogonal to where the categories are getting embedded, okay? So if you think, I mean, this is all very rough and hand-wavy, but if you think of this category as a sort of two-dimensional thing, something like a kind of sheet, then, you know, it gets sent somewhere under F and somewhere under G. And then in some sense you can think of these components of the natural transformation as being kind of orthogonal to the arrows in these two-dimensional planes. Okay, so I want to talk about another example of natural transformations that we can have a look at, which is kind of simple, but it's a nice example to look at to understand what kinds of things we can do with natural transformations, and it's going to be very useful for us later when we talk about limits. So I don't want to get too much into limits yet, but essentially this concept of limits generalizes the kind of things we were talking about products. So we can find lots of other kinds of substructures in categories that represent all kinds of interesting mathematical operations. So limits are a very interesting topic, but now I just want to introduce the sort of underlying relationship with natural transformations. A natural transformation goes between two of these kind of functors, which are sort of, we can think of them as parallel arrows. So we have a functor which I'm calling delta Q, and another functor called G, and a natural transformation from delta Q to G. Normally natural transformations are written with these sort of double arrows because they're kind of arrows between arrows if you want to think of them in this category cat. Okay, so what is this delta Q then? Well, this is what's called a constant functor. So essentially it just maps all of the objects in C into Q and all of the arrows in C into IDQ. So it's going to look like this. Okay, and if you know, it'll send this arrow F into IDQ, this arrow D and G into IDQ, and so on. Everything gets collapsed onto Q and its identity arrow under this constant functor, just like a constant function sends all of its inputs to a constant. This functor sends all of the structure of our category into the stuff around this single object Q. So that's going to be one functor, and the other functor, let's just say it's something general. I'm just going to pick something which preserves this structure exactly because it's easier to draw. So let's say this is our other functor G. So then what's a natural transformation going to look like from the constant functor to G? Well, remember the definition. For every object I in C, this natural transformation is going to have an ith component, which is going to go from delta Q of I into G of I. And what's delta Q of I? Well, this is just going to be equal to Q, simply. So for every object I, we're going to have an arrow from Q into G of I. So that'll be alpha I, that'll be alpha K, and that'll be alpha J. Now, what's the other condition we need for this to be a natural transformation? Well, we need to have commuting squares for every arrow in our source category. Okay, so what does the commuting condition look like for this kind of natural transformation? Well, we know that for every arrow F from I to J, under G, this is going to get changed into G of F, which goes from G of I to G of J. And under delta Q, of course, we're going to have delta Q of I goes to delta Q of J under delta Q of F. So our definition of a natural transformation means that we require these components, alpha I and alpha J, to make this kind of diagram commute. Okay, so going along this arrow and then this arrow, composing, gives you the same thing as going along this arrow and then this one. But we can simplify this a bit, okay, because we know how delta Q works. So we know that delta Q sends every object to Q. So we know that delta Q of I is just going to be equal to Q. And delta Q of J is again just going to equal Q. And what does delta Q do to this arrow F? Well, it sends it to the identity. Okay, so this is just going to be the identity arrow of Q. So let's write down the condition that we get for this square having to commute. So what we get is that G of F after alpha I, that's this way, is equal to alpha J after IDQ. That's this way. And we can simplify this a bit because we know that when we compose something with an identity arrow, we just get the other arrow back. So this is just going to be equal to alpha J. And actually we can write this kind of equation here a bit more simply because, I mean, why are we bothering, we can ask ourselves, why are we bothering to write two copies of Q with this kind of do nothing arrow between them? I mean, if we just collapse this diagram and we just put Q up there and we say that now this triangle has to commute, so we sort of got our commuting square and then squashed the top together, we can just say that this triangle commutes here. And that's just what we've written in this equation. So you might remember we encountered commuting triangles like that when we're talking about products. And we're going to encounter a lot more when we talk about limits in the future. I mean, this kind of construction here, where we have a natural transformation from a constant functor to another functor, is often called a cone. You know, it's called a cone for sort of good reasons. This looks like a triangular based pyramid in this case, and you know, in general you'll have some category and then you'll have some sort of another object at the top which you're using as your as the image of the constant functor, and then all these natural transformation arrows kind of rain down like a big cone of arrows coming down onto the target of the functor G. So all of the kind of triangles of this pyramid or cone or whatever you want to think of it as have to commute, and that's the nature of this kind of natural transformation from a constant functor to another functor, and we're going to encounter these in a lot more detail when we study limits. Okay, so remember I said that these natural transformations can be considered to be arrows between functors. Well, if that's true in the same sense as I've been discussing arrows so far, then we ought to be able to compose those arrows together, right? So how do we compose natural transformations together? Well, there's a couple of ways to do it. There's so-called vertical composition of natural transformations, and there's also something called horizontal composition of natural transformations. So I'll start by telling you about vertical composition. So in this category of categories, suppose we have a category C and a category D, and let's suppose we have various functors from C to D. So say we have these three kind of parallel functors here, F, G and H, and these are all going from category C to category D. Well, there can be scenarios where we might have a natural transformation alpha from F to G, and we may also have another natural transformation, say beta, from G to H. So in that case, we can compose these two natural transformations together, and that's going to result in another natural transformation which is going to go straight from F into H, okay? So this makes sense with our thinking of the way composition normally works. And we will denote this new sort of composition as beta dot alpha. So this is the so-called vertical composition of alpha and beta, and it's just called vertical because there's a kind of convention that normally we draw these diagrams this way round. Vertical composition is really composition of natural transformations between parallel functors, and you'll see what the other kind is later. Notice that we're denoting this here with a solid dot, so this is another important convention. We're not using an open circle here, we're using a solid dot. And so how is this vertical composition defined? Well, it's going to be a natural transformation from functor f to functor h, and it has a very simple definition. So the definition is simply that the eighth component of this vertical composition is just going to be the eighth component of beta composed after the eighth component of alpha. So I suppose the first thing I need to convince you of is that this thing defined like this actually is going to be a natural transformation. So of course we have a picture like this, so it is going to lead to a family of arrows which go, so the eighth component of this transformation is going to go from f of a into h of a. So it's these arrows have got the right source and the right target, but they need to satisfy the other condition for them being natural transformations, and that is that they make these squares commute when we consider the arrows, okay? So what I'm saying is that if we have an arrow f from A to B in this category C, then there's going to be a sort of square that we're required to commute associated with that. So we can see that this works out okay by looking at this diagram here. I mean, we know that alpha is a natural transformation from functor f to functor g. So if we consider a general arrow, little f in C, then we know we're going to have a commuting square like this. We know that if we go along f of f and then alpha b, that'll give us the same thing as if we go along alpha a and then g of f. In other words, we know that this square commutes. Similarly, because this is a natural transformation, we know that this square commutes. So going along here and here is the same as going along here and then here. So what we then have to show is that this is a natural transformation. So we have to show that this big kind of square commutes. And we can do this using what they call diagram chasing, okay? So it's a very simple idea. It's just basically that we sort of point at the diagram and use the fact that we know that some of these paths commute with some of these paths give the same answer, and slowly we're able to show that one of these paths gives the same result as the other one when we compose all of the arrows along the paths. So I'm saying that what we want to show is that if we go along f of f and then alpha b and beta b, we get the same thing as if we go along alpha a and then beta a and then h of f. So if we go along this path, like this, well, since we know that this is a commuting square, we could instead traverse this path like this. We could go along here first, and then we can go along here. Okay, so we can change it into this path. And then since we know that this square commutes, we know that doing this step and then this step would be the same as this step and then this step. So we know that this path has got to be equal to the one that just goes like that. And that shows that this big square also commutes. So indeed, this will give us a natural transformation as a result. I've now told you that we can compose these natural transformations. And so if we consider all of the natural transformations between all of the functors that are sort of parallel going from C to D, can you guess what kind of structure those form? Well, they indeed form a category. I mean, we can actually think of every object as a functor and each of these natural transformations as an arrow between functors, okay? So this is a remarkable idea. So we can sort of reinterpret this to say, well, F is a functor, we'll think of that as a point. G is a functor, we'll think of that as a point. H is a functor, we'll think of that as a point. And then we're going to have these natural transformations, which we can now think of as arrows between functors. Okay, so I've told you we can compose these natural transformations vertically. I'll leave it up to you to check that composing these natural transformations vertically is an associative thing. Remember, in order for this type of thing to be considered a category, we have to have the arrow composition is associative. Now, the final thing that we need to know is, well, what are the identity arrows? What's the identity arrow in this kind of category? So that would be somehow a natural transformation which can send a functor to itself. So if we have a functor F, from a category C to a category D, we have a natural transformation which I like to call 1 superscript F. So that's going to be a sort of identity natural transformation from this functor F to itself. So over here it'll look like this. In this picture, I suppose we draw it like this. But what is this natural transformation? We know that it goes from this functor F to this functor F. But how is it defined? Well, it's defined such that its 8th component is just going to be the identity arrow of f of a. So remember that so it's defined like this. It's going to have a component, of course, for every object of C. This is what I propose we have as an identity arrow in this kind of category here. So this can be considered to be a sort of natural transformation from a functor to itself, a kind of identity natural transformation for a functor. So remember, we better have that the eighth component of our natural transformation sends f of a to f of a. So using the identity arrow of f of a seems like a very sensible idea for trying to make a sort of identity natural transformation. So let's just check that this is indeed a natural transformation. So we'll consider an arrow f from A to B in this category C here. Now under f, this is going to get sent to f of A, f of f, f of B, and under another copy of f we'll get the same thing. And so what we're going to want in order for this to be a natural transformation is for this kind of square to commute, okay? Because a generic arrow f in this category C gets sent to this kind of arrow under f, and it gets sent to this kind of arrow under f. And so clearly if we have this sort of the eighth component of what I'm proposing for an identity, if we have this as ID of f of A, and this is ID of f of B, then that's clearly going to make this square commute, isn't it? Because composing with the identity isn't going to really do anything, so we're just going to get that f of f equals f of f. So each square associated with an arrow in C is going to commute. So this is indeed a natural transformation. And so now I'm basically claiming that we have another category, okay? So this is a sort of category inside this category of categories. So basically I'm saying that if in this category of categories we'll have a category C and a category D, and we can consider this family of functors from C to D. And if we consider all such functors, we'll have natural transformations between them. And now we can do vertical composition upon them, and we have ideas of what we might consider to be identity natural transformations. So I'm now arguing that this whole collection actually constitutes a category itself, okay? So let me write that down. Oh, I also want to say this convention here of writing this identity natural transformation associated with functor f, I like to write it as like one with a superscript f, so an f upstairs, but that's just a personal convention. Otherwise I find it gets confusing when you've got subscripts representing components of natural transformations, but please note that's just a personal convention you may not wish to adopt when you're doing category theory. But yeah, so we have this interesting kind of new structure now that we see within this category of categories, and we write that as d to the power of c. And what this essentially is a category where all the objects are functors, which go from C to D. And then the arrows in this new category here, this thing, are going to be the natural transformations between these functors. And the way that we compose these arrows is this vertical composition of natural transformations, which I have defined. And as identity arrows, we have these kind of identity natural transformations as defined up here. So I'll leave it up to you to convince yourself that this is actually a category. We just need to show that this kind of thing is a well-behaved type of. It acts like an identity arrow, in the sense that if we do a vertical composition of it with any other natural transformation between these kind of parallel functors, then we'll just get that other natural transformation back again. And we also need to show that composing, like doing vertical composition of these natural transformations, is going to be an associative kind of thing. So this kind of category here is usually called a functor category, or we could call it the category of functors from C to D. And it's basically just a category where every object is a functor and the arrows between them are natural transformations. Okay, and these are all parallel functors, and we're composing these natural transformations with vertical composition. And so it's kind of interesting that we have these different kind of levels to look at things on now. I mean, you start to get a lot of appreciation for what a rich object this category of categories is. I mean, we can kind of zoom out as much as possible and look at it with this kind of picture here, where the categories are kind of dots and or objects, and the arrows between them are functors. And in that case, these natural transformations are kind of arrows between arrows, if you like. We could, of course, always zoom in to look in to particular objects and look at what category that represents and see what kind of structure is within there. That's another thing we can think about in this category of categories. We can also now, and then we can also look at one of these natural transformations, let's say alpha here, and then we can kind of say, well, what does that natural transformation actually mean? And then we can look at its components and think about things like these commuting squares and what this means for the individual kind of objects and arrows within, you know, where the things in C get mapped to in D, and how these components of this natural transformation alpha appear as components within this category D. So we have that view as well. And now we have yet another view, another picture, which is to think about all these kind of arrows going from C to D, all of these functors, all the possible functors from C to D, and that gives us this kind of category, which gives us this sort of picture here, where now we have objects representing the different functors, and the arrows between them are now these natural transformations. So we have like many different viewpoints to look at things from, and you know, a lot of category theory involves sort of moving from one viewpoint to another as is convenient for the type of reasoning you want to do. And so it's very interesting to get used to this kind of notion of like viewing these structures from lots of different perspectives. Okay, so this is a point in the series I've really been looking forward to, because I'm finally going to complete the description of natural transformations. And this is really a kind of this is really a kind of special point in explaining category theory, I think, because I believe that categories, functors and natural transformations are really the main ways that category theory is described. So once we've finished understanding the basic ways to combine natural transformations, we've really got enough language to be able to delve in and see these really deep ideas in category theory at work, and we'll have all the, or most of the language necessary to discuss such things. So the final thing then I need to tell you about natural transformations today is the notion of horizontal composition. So the basic idea is that, say we have a couple of functors f and f bar, and they both go from a category C to a category D. And then we have a couple of functors g and g bar that go carrying on from D into category E. So we could compose these two functors together and we'd have another functor like this, G after F. And similarly, we can compose these two functors together and we'll have another functor here, G bar after F bar. So what's the horizontal composition of this natural transformation alpha and this natural transformation beta? Well, it's actually a natural transformation which goes from this functor G after F to this functor G bar after F bar, and we call this beta circle alpha. Okay, so when we're talking about horizontal composition, we use an open circle, and when we're talking about vertical composition, as we were previously, we use a sort of filled in circle, a kind of big dot. Anyhow, yeah, so this is essentially the same thing as I've illustrated up here, just in words. But of course, I still have to tell you how this horizontal composition really works. I mean, this is a natural transformation, so it can be thought of in terms of components. I mean, that's where the real essence of the definition of a natural transformation lies. For every object in C, there's going to be a component, an arrow of E, which is going to be called beta after alpha of A. And I need to tell you now how we can get that by looking at alpha and beta and these functors. So I'm going to describe that next. So I'm going to go through a construction where we're going to determine what the components of this horizontal composition of natural transformations are. This is, in my opinion, a fairly important construction. I certainly use it quite a lot. I mean, often when you're looking at books on category theory, they talk about this horizontal composition of natural transformations using very little equations, but to really understand what it means, you have to kind of expand it out and look at how these natural transformations work in terms of components. You know, what are the arrows, what are the components of these natural transformations? And so I find myself having to draw this picture or imagine it over and over again in order to understand what's going on. So let's have a look. So we start with an object A in this category C, and we'll apply this functor f to it, and we get f of A. So over here, this is in category C. The other thing we could do is apply this functor f bar and then we'll get f bar of a. Okay, so I've just redrawn the picture here so we can compare with it as we're discussing how to create this, how to find these components of this horizontal composition. Okay, so at the beginning we have an object of C, and we can send it to something using F, or we can send it to something using F bar. And then we know that there's going to be a component of this natural transformation alpha, which is going to send f of a to f bar of a. So that's what's going on in this category D here. The next step is to then apply these functors G and G bar. So they can give us different things. So when we apply G to this stuff, we'll get G after f of a and G after f bar of a. And remember, functors also operate on arrows. So this component of this natural transformation here is going to get lifted to an arrow over here. And that's just going to be G of alpha of a. So that's one thing we can do. The other thing we can do is instead apply G bar. So if we instead apply G bar to this, we get G bar after f of a, and applying G bar to here, that'll give us G bar after f bar of a. Okay, and again we're going to lift this natural transformation component here. So that becomes G bar of alpha of a. So there's still more that we can draw in, because we also know that there's going to be this natural transformation here, beta, which is a natural transformation from G to G bar. So here we have some object of category D, okay? So this is category D. What's going on in here is category E, okay? But in category D, we have this object here, and it gets sent to something under G, and it gets sent to something else under G bar. So the f of a component of beta is going to be an arrow which goes from here to here. This is going to be beta of f of a. Okay, so remember that the component of a natural transformation associated with something in an object in the source category goes from where that object got sent to under the first functor to where that object got sent to under the second functor. Okay, so our first functor is G, our second functor is G bar. So this is going to be an arrow, beta here is going to be an arrow from G after f of a to G bar after f of A. And similarly, we have an object over here in this category. It gets sent to G after f bar of A under G, and it gets sent to G bar after f bar of A under G bar here. So that's going to be an arrow like this. So this is going to be beta of f bar of A. Okay, so we've done all of this. Now, what are the components of our natural transformation we're looking for? This horizontal composition thing. Well, remember that we wanted something which went from G after F to G bar after F bar. Well, how about this arrow here? This arrow goes from G after F of A to G bar after F bar of A. So why don't we just call this beta after alpha of A? So this is the 8th component of this horizontal composition of these natural transformations. So it's an arrow from here to here. But, okay, how do we actually make this arrow though? Well, there's actually 2 ways we can do it. So when I write this arrow, I'm saying that it represents the thing that we get by either going along here and then here, or by going along here and then here. And in fact, it doesn't matter which one of those we do, because beta is a natural transformation. So we know that going along beta of f of A and then G bar of alpha of A is going to be equal to what we get, you know, when we compose those together, we'll get the same thing as if we go along G of alpha A followed by beta of f bar of A. So what I'm saying here is that this is the crucial sort of definition then. So the critical thing I'm saying here is that the 8th component of this horizontal composition, it can be written as G bar of alpha of A after beta of f of A or it can be equivalently written as beta of f bar of A after G of alpha of A. So we have these 2 kind of options about how we want to express this composition, but it basically comes from this kind of picture where we start with an object, we say, well, how could it get sent under F and how could it get sent under F bar? So we have these two possibilities. And then again, we see how those two could be sent to different things under G and G bar. And then we end up with this kind of square here. And then we just say, well, we want an arrow that goes from G after F to G bar after F bar. So we can get it by going along two sides of the square, either these two or these two. And either way, composing those gives the same thing. And we call that the 8th component of this natural transformation, the horizontal composition of alpha and beta. Okay, so that really finishes the kind of core definitions that we need to know to do a lot of category theory. I mean, one thing that you may want to do, it's a really nice exercise, is to actually convince yourself that this is a natural transformation. I mean, all I've done so far is basically told you what the components of this natural transformation are. But how do we actually know it is a natural transformation? Well, it's a big drawing exercise. It's quite fun, really. It's not really conceptually that hard. All you have to do is you start with this and then you go, okay, what if we've got an arrow F that goes into an object B? And then again, you kind of branch out a similar structure to what you have here. And then you can sort of do a lot of diagram chasing, and you look at this blue arrow up here, there'll be another similar blue arrow you get down here related to B. And then you've got to convince yourself that you have one of these kind of naturality squares, you know, these commuting squares that we require to be present for these natural transformations. And so you can do that and convince yourself that, yes, this is indeed a natural transformation when it's defined like this. Okay, so that's the kind of definition absorbing part over with now. And we can just discuss some of the many wonderful properties of these natural transformations. So we already saw earlier that we could compose these natural transformations vertically, and we saw that that reveals extra structure within this category of categories, because when we thought about all of the parallel arrows from one category to another, all the functors from C to D, we realized that we could actually think of those functors as objects within a kind of functor category, with the natural transformations as arrows between them, with vertical composition. But now we have this new idea of horizontal composition of natural transformations, and it turns out that that reveals yet more kind of hidden category structure in this category of categories, because we now have another way, now have another way of composing these natural transformations. We can compose them horizontally. So when can we do that? Well, we can compose a natural transformation alpha with a natural transformation beta horizontally when alpha goes between some parallel functors and beta goes between some parallel functors, and parallel functors of the first kind are composable with parallel functors of the second kind, in the sense that these end where the next functors, the G and the G bar, begin. So we know when we can compose them, and now we know how to compose them thanks to that last diagram. So guess what? We have another category. So there's another category which has objects as categories and arrows as natural transformations, which we can compose horizontally. Okay, so we can think, if we like, of this alpha here in some sense as being a sort of arrow from C to D. And we can think of this beta in some sense as being a sort of arrow from D to E. And we can compose them together. And remember, when we compose them, we get an arrow which goes from G after F to G bar after F bar. And that can be considered to be an arrow from C to E. Well, it turns out that horizontal composition of natural transformations is associative. Okay, so we have this kind of condition. When we have these parallel functors in a chain like this, we have that gamma after beta after alpha equals gamma after beta after alpha. So we have associativity with these new arrows. What about identity arrows? We need to have identity arrows. So what's going to be an identity arrow? Well, it better be a natural transformation that somehow we can think of as a sort of arrow from an object to itself. In this case, the objects are categories. So what kind of thing can we pick? Well, we know that this category D here is going to have an identity functor. Okay, so here is where we have two different notions of identities. We have identity functors and identity natural transformations, and they're both playing a part in these ideas, so we can see the difference between them. So remember, the identity functor is just something that sends every object of D to itself and every arrow of D to itself. Now also, we have an identity natural transformation from that identity functor to itself. Okay, so remember, for a functor f, I'm writing one superscript f to denote the identity natural transformation associated with that. So here the functor in question is this thing here. Okay, this identity functor. So it turns out that a natural transformation like that operates as a sort of identity with respect to this horizontal composition. And again, you can convince yourself of this just by drawing out a version of that diagram that I just described. So essentially what we're saying here is that beta horizontally composed with the identity natural transformation associated with the identity functor is going to be equal to beta. And also, if we get this identity thingamajig and we do that after alpha, then we're going to get alpha. So these are the, I urge you to try and convince yourself of these truths. But essentially, these are what we need to know that there's yet another category here, a category which has the sort of categories as objects and these natural transformations between categories as arrows, but this time we do this horizontal composition. So there's really so much to the idea of natural transformations. I mean, they have their interpretation as kind of arrows between parallel functors, and they give us this notion of a kind of category of functors from one category to another, and we also can compose them horizontally. Okay, so they're really very expressive kinds of objects. So just to sort of demystify how this identity natural transformation of the identity functor works, I've just drawn a little diagram here showing the naturality square which comes about, and it's everything ends up very simple in this case. Okay, so now the final thing to say is about how this notion of horizontal composition of natural transformations and vertical composition of natural transformations relate with each other. And this is something called the interchange law. And so basically this is the law. Okay, so remember, the solid circle denotes vertical composition and the open circle denotes horizontal composition. So we have a kind of situation like this. We have a category C and a category D, and in this case we have these three parallel functors, F, G and H, all going from C to D. And similarly we have F bar, G bar and H bar. They are functors going from D to E. Now we have some natural transformations here, alpha and beta, and we can vertically compose those. They're between these F, G and H, and we have alpha bar and beta bar playing similar roles over here. So we can compose these things together in different ways, and the interchange law tells us that they're associated.